x. And the y-intercept over here is equal to 0. So there's no y-intercept at all. Or the y-intercept is equal to 0. So I'm going to call this my equation number 1. So the next step, once we have this, right? So we done this already, right? We have done this, right? We have done this. So we're going to use dv by dx equal to minus omega x. So we're going to substitute into. So we have dv over dx is equal to minus omega as a function of x. So this will be equal to minus omega naught over Lx. Okay, so this is my equation number 2. So the next thing we're going to do, we're going to integrate. All right. So v as a function of x now is equal to minus omega naught x squared divided by 2L, right, plus by C1. Okay, so this is our equation number 3. So from here, can we solve for C1? No, because we don't know our boundary condition for V when x is equal to 0. We also don't know our boundary condition when x is equal to L. Okay, we did not determine. You want to determine is easy. You just do your your static analysis. Okay, but we did not do that for this case. So from here, we integrate the second time. So we know, so we know that this entire term over here is equal to dm by dx. Okay, so this is my equation number 3. So we're going to integrate again. So what we have is moment as a function of x is equal to minus omega naught x cubed over 6L plus by C1x plus by C2. So this is my equation, our equation number 4. So with equation number 4, right, we can find what is our C1 and C2 because we are going to use our boundary condition number 1 and we're also going to use our boundary condition number 2. Okay, so we're going to substitute when x is equal to 0 and m is equal to 0 into equation number 4, right? So from here, you know that C2 is equal to what? 0, right? So you have a good practice is once you have used this boundary condition, put a tick to know that you are done with it. Okay, you cannot use, if you have the same equation, you cannot use the boundary condition twice. It does not work at all. Okay, so put a tick down there. So you know that, so this will be equal to, therefore, m as a function of x is equal to minus omega naught x cubed over 6L plus by C1x, right? Because C2 is equal to 0. So because this equation is evolved from equation number 4, we call this 4a. Okay. Then next, we can in fact find C1 also. To find C1, we have to substitute x is equal to L. All right, the moment is still equal to 0. And then we're going to substitute into equation 4a, right? So x equal to L, moment is equal to 0, what are we dealing with? Okay, what are we looking at? So we are looking at boundary condition number 3. When x equal to L, m is equal to 3, or m is equal to 0, that's boundary condition number 3. So from here, we will have 0 is equal to minus omega naught L squared over 6 plus by C1L, right? So therefore, C1 is equal to omega naught L over 6. Okay, so that's our C1. So from here, you get, therefore, the moment as a function of x is equal to minus omega naught x cubed over 6L plus by omega naught L over 6x, and this is equal to EI d squared y over dx squared. Okay, so this is our equation number 4b. So when we introduce this relationship over here, okay, with respect to m as a function of x, so what we immediately just did, okay, we have applied, what we have done is we have applied the elastic curve theory. Okay, so from here, right, so what we have done is we have found two are constant. We have exhausted two of our boundary condition. Okay, boundary condition number 1, boundary condition number 3, and now we have applied the elastic curve theory. We let the whole equation to be equal to EI multiplied by d squared y over dx squared. Then what we do next is we integrate again. And the integration is nothing complicated. It's really straightforward. Okay? We're going to integrate again. So you have EI dy by dx. So this is equal to minus omega naught x4 over by 24L plus by omega naught L x squared over 12 plus by C3. Okay, so this is equation number 5. So you realize that EI dy by dx is in fact I'm going to write, I should leave more space a bit. Okay. So this is also equal to EI theta. Okay, which we know, which I did explain, is equal to equation of the slope. And then finally, we integrate one last time. We have EIY. Now, from equation number 5, we cannot solve anything. Yes, we cannot determine C3 because from this function over here, from the boundary condition that we have nothing in terms of theta. Okay, nothing means we don't know what is the value, or it is not equal to what? It is not equal to 0. Okay, we don't know what is the value, and we don't know, and we also know that it's not equal to 0. So from here, you have equal to minus, right, omega naught x5 over 120L plus by omega naught L x cubed over 36 plus by C3x, and then finally plus by C4. Okay, so this is your equation number 6. So we're going to substitute when x is equal to 0, y, the deflection is equal to 0, into equation number 6. Right? So for this case, x equal to 0, y equal to 0. So your x distance is equal to 0, y is equal to, so it's boundary condition number 2. Right? X is equal to 0, y is equal to 0. So from here, we know that C4 is equal to 0. So therefore, EI y is equal to minus omega naught x5 over 120L plus by omega naught L x cubed over 36 plus by C3x, and this is your equation 6a because it evolved from equation 6. Okay, and then we're going to substitute our last boundary condition, like what we have said. We have 4 unknowns, we need 4 boundary conditions, so we're going to substitute. I'm going to do side by side. So I'm going to divide the page into 2. So we're going to substitute. Right, hold on. We're going to substitute. I'm going to copy the whole thing. I can't see it. And if I can't see it, neither could you. Okay. Copy. Paste. Right. So we're going to substitute. So therefore, This is equal to 0. Then this is, did I say we're going to substitute the boundary condition? Oh no, not yet. So we're going to substitute x is equal to L, y is equal to 0 into equation 6a. Okay, we're going to do, so the last boundary condition. So x is equal to L over here, y is equal to 0. So we have used the last boundary condition. So from here we have this will be equal to 0 is equal to minus omega naught L4 divided by 120 plus by omega naught.
Isn't it L to the 5?
Oh yeah, no, L to the 4, because L below 5 on top we cancel, right?
Oh yeah.
Okay, over 36. I'm glad you are awake. Okay, I like that, because I'm nearly falling asleep now. Plus by C3L. Okay, so this is what we have. Blah 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 blah. So now we can find our C3, right? We can determine our C3. So C3 is equal to 1 over 120 minus by 1 over 36 is equal to minus 7 over 360. So is equal to omega naught L cube, right? Because C3L has L on the left hand side, L to the power 4, you bring it down, C3 is L cube. So therefore, once you have this, voila. Okay, so therefore, y as a function of x is equal to minus omega naught x4 over 120L plus by x5, sorry, x5 plus by omega naught x4 over 36, right? And then plus by, sorry, x3, not x4. Okay. Or Lx cube, sorry, Lx cube. And then the last one is minus 7 over 360 L cube. Okay. So the whole thing, you bracket, because it's now y as a function of x, you have to divide by the whole term by 1 over EI.
For C3, are you missing omega? Is it omega naught on the last term? -7.
I am. Thank you.
No problem.
Okay, so yeah, both. No, this is correct. Yeah, omega naught L cube. So this is our equation 6b, right? And then we also know that our slope theta as a function of x is equal to 1 over EI, and this will be equal to minus omega naught x4 over by 24L, and then plus by omega naught L x squared over 12, and minus 7. I think I'm missing another term. Hold on, and I'm missing another term down here. Yeah, C3x. Sorry, my bad. Small paper. You have to have an x down here. And the last one is 7 over 360 omega naught L cube. So this is from, so there is theta x, and that will be equal to equation 5a. Okay, 5a. So this is equation 6b. Okay. So let me check. Yep. Right. So that's it. Okay. Just integrate 4 times. Very, very straightforward technique.